is Angelo Tartaglia. The title of this talk is Relativistic Positioning as a Complementary Technique of Laser Ranging. And this is done by remotely.
Yeah. Well, thank you.
Yes, okay.
Good evening, everybody. And as Feliciana told you, this activity is made within the scope of the collaboration Galileo for Science. In this case, the group is mainly working in Turin. And okay, the title of the presentation tells you what the subject is. What is meant by relativistic positioning? You know that space-time is Riemannian manifold, curved Riemannian manifold with a Lorentz signature. We may think of it here in the picture, it is just 1 + 1 dimension. That's sort of background, wavy background, where there is a texture made of essentially of null geodesics, light rays, if you like, or the null wavefronts. Oh, well, apparently. Is this visible? Well, we tried it before. It was working indeed. Yeah. Yeah, yes, I'm trying. Apparently, it tells me that I'm sharing. Is it? Well, I'm trying many times, so let me try again. Is it visible now? I don't know what to do. Well, yes, I try to do this, but now it's the whole screen. I'm starting again the presentation. Yes, everything was okay. I don't understand. I'm doing the same things. Okay, I'll try. Yes, okay.
Can I say this? Okay. I would like to propose a swap the order of the presentation. So can you possibly send the presentation to the organized committee?
Let me try again too. I'm trying now.
Yes.
Angelo,
Yeah.
what about we swap the order of the presentations and you do these 15 minutes
sure.
later and you keep trying them in the meanwhile to sort these problems? Yeah? Oh, no, look, Angelo, it's working now. Please go ahead, forget what I said.
Well, anyway, I was here. You see space-time as this wavy blue background. The white lines are null geodesics. They are a texture which describes the geometric properties of space-time. If you choose a given reference frame, an appropriate reference frame, you may use this texture, in a sense, to localize the events on the space-time, in the space-time. So in particular, we have the possibility. This is a sort of a little section of the. Here it is flat. You have an observer who has a word line here. There's the reddish one here. And you have the wavefronts, null wavefronts, which are signals sent by, in this case, because it is 1 + 1 dimension, by two different emitters. You should know where the sources are and also the frequency at which they send you the signals. Then you just have to measure with your own clock on board the arrival times and the sequence of the arrival times. Then there is a simple algorithm that allows you to localize to find your position with respect to the starting point where you move from. But this is sort of the positioning for navigation. In our case, we are speaking of the Galileo and in particular of Milesa and Milena, which went astray. So the idea is to use the localization, the positioning bottom up. I mean, the emitter is in space here. The receivers are on the ground, and the receivers are in well-known positions. You know the coordinates. The receivers have synchronized clocks. They are measuring the arrival times of the signals coming from the emitter. And this is what you know. Using this data, you have to determine to calculate the position of the emitter in space and time. Of course, the red lines are light rays. We are, for the moment, in a flat Minkowski space. Of course, the light rays are on the light cone, the future light cone of the emitter. And we should also consider that we are using non-rotating reference frame centered on Earth, but the receivers are on the surface of the Earth, so they are rotating. So here, but it is not visible in the picture, you should draw also the word lines of the various receivers. They arise as helices, which are intersecting the light cone. Now, what are the basic equations to use this approach? As far as we are in a flat space-time, you use Cartesian coordinates in an Earth-centered non-rotating frame. The equation of the null geodetics is very simple, is even trivial. The one you can see here, where the index I is goes from 1 to 5. Actually, we have 4 dimensions and 4 unknowns. So in principle, you can do it using just 4 equations, but I will use 5 for a simple reason, just to simplify the next steps. What can we do? Suppose you are writing your 5 equations like this, then you subtract one equation from the other in pairs. Let's say we subtract the first equation from the second, and then from the third, the fourth, and the fifth. You are left with a system of 4 equations in 4 unknowns, where the squares of the unknowns have disappeared. So the system you are left with is a linear system And the index here, the J, is now running from 2 to 5. Now this solution of a system like that is very simple. We have the vector of the unknowns here, this xi. You have the coefficients of the unknowns, which are explicitly written here in this matrix C. Then you have the known terms, what you know here, where for short, instead of explicitly writing the sum of the squares of the x, y, and z, we have written the distance from the square of the distance from the origin of the reference frame. You have just to calculate the inverse matrix of C, and then multiplying by that, you obtain the solution, just combining, multiplying the inverse C times n. Of course, this inverse matrix is simply simple to calculate, provided the determinant of the matrix is non-singular, which means in practice that the points that the receivers you are using should not be aligned, for instance, or things like that, which is just proviso for the choice of the receivers. If you want to make explicit the fact that the receivers are indeed moving because the Earth is rotating, you can write down the same thing using polar space, polar coordinates, where you have the angular velocity of the Earth. And so you have explicitly the dependence on time, on coordinate time of the x's and y's of the receivers. Now, what about gravity? Because of course we know that all this doesn't appear in empty space-time, but it happens on Earth. We can do again here, just to evaluate orders of magnitude, a simple approximation. Let us suppose that the space-time is a Schwarzschild space-time. And in this case, if even again, to simplify and to have an order of magnitude, let us consider a radial null trajectory, which allows us to integrate exactly the trajectory. And we are left with this result. Time of flight is here, and here are the different radii from where the signal is started. Here you are considering, for instance, the first receiver, so I have the index 1. Of course, m is the reduced mass. Now, the difference between flat space-time and this result is, of course, the term which contains m. Let us evaluate the relative importance of this correction with respect to the flat situation. The result is here, and if you expand in powers of m divided by r, you are left with this. And you see that this correction is in the order of some units in 10 to the 10th. Well, is it good or is it bad? This is not bad, of course, there is more to say, but if you want, you can go at upper levels of the development, but it's useful to know that this is the order of magnitude you can obtain. If you want to consider another aspect, is that, of course, your clocks at the receivers on the ground are not measuring the coordinate time, of course, but their proper time. And so again, you have to go to now a rotating reference frame, which is co-rotating with the Earth and the receivers. And in this case, since the receivers are not moving on the surface of the Earth, the relation between the coordinate time and the proper time is the one you see here. Theta is the co-latitude surface, the tangent speed with respect to the speed of light. You see that this is 10 to minus 9. This is in the order of 10 to minus 13, you have a small little correction you can use to convert the numbers obtained reading the clocks of the receivers to the coordinate time, which you use for the other calculations. Now, there is something to be considered concerning uncertainties, errors, and so on. So far, we have seen that we have an analytic solution, of course, but the parameters you use for describing a solution contain information which is cannot be exact. So you have to account for systematic errors. You know where the surface stations are, but of course your knowledge is affected by some systematic error unavoidably. You have to measure the time with the clocks. Again, you have some systematics, and also you have an uncertainty coming from the measurement process. And well, of course, if we want really to use this approach, we have to consider that light rays or radio waves are traveling not in vacuum, but through the atmosphere. So you have to account also for a refraction index and things like that. Well, this is the essence of the method we are working now on, and we are trying to consider practically the aspects of numbers and well, accuracies, precisions, and the like. This is all I wanted to tell you, and I thank you for the attention.
Thank you very much. Do you have